Okay, thanks for the chairman and thanks for every audience waiting here. It's my pleasure to introduce my work here. My presentation is Peridynamic model simulation of string softening in elastic damage problems. The presentation includes 4 parts, that is motivation, peridynamic model of string softening, numerical test, and summary. So first, let me give a explanation of the definition of string softening. As the red curve shown in these figures, it is obtained by displacement control. It includes 3 stages. For the first linear stage, the load and the displacement has a linear relationship. And at the second stage, the linear relationship disappears and the load is still increased with the increasing displacement. This stage is denoted as string hardening. At the third stage, when the PQ value is reached and the load decreases with the increasing displacement, this stage is called string softening or tension softening. This phenomenon is easily found in ductile materials such as concrete. Well, for these materials, if they are under load control, the load and the displacement curve is like the green curve in these figures. The string softening phenomenon has attracted people's attention for many years ago, especially with the development of numerical methods such as finite element method. The figures here is obtained by the FEM. From this figure, you can find that when the mesh density is increased, the results of the damage is seriously sensitive to the mesh density. So this phenomenon is called mesh dependence. The mesh dependence leads to the consequence of string localization. That means the string softening damage tends to localize in the zone of vanished volume. So this is the problem. At first, people, in order to solve this problem, have proposed many methods such as impose a lower limit on the element size of a string softening bond of a values in the embedded FEM, or consider a length of damage characterized by the stress displacement. All these 3 methods is the improvement in the numerical method, but later people found that this problem is not caused by the numerical method. It is due to the local continuum mechanics. So people later introduced the non-local interaction to adjust the deformation of localization. This method is denoted as the non-local continuum approach. The approach is finished by this non-local version offered with the non-local weighted function. Based on these basic ideas, many non-local damage formulations are proposed and listed in this table 1, such as the results of one of these non-local damage model. We can find that the results are not related to the mesh density. Where n is represented the mesh density as n increases, we can find that the softening zone is not related to n. So we can find that this non-local approach overcomes the mesh density, but we can find that the governing equation is still local. That means that the non-local equation is not actually considered. In the redundant research of Sterling point that by a simple composite structure, he found that a non-local term naturally arises in the governing equation when the detailed macrostructure is described by a most displacement field, while the governing non-local equation has the same formulation as peridynamics. Then he used this non-local equation to solve a composite plate with a hole. The results of the non-local model is consistent with the experiment data, while the results of the local model, I show the red curve in these figures, is very different from the numerical data. So based on these reasons, we may think that maybe a constant non-local density model based on the framework of peridynamics is more practical and maybe more useful. That it can make sure the governing equation and the non-local damage parameter is both non-local. So before we do this, let me make a simple introduce about the peridynamics. It is a new theory. It is a kind of integral type continuum mechanics. In peridynamics, a mature point has interactions with its neighborhood, has interactions with any mature point in this neighborhood. This neighborhood is described by a sphere in three-dimensional problems with radius L. L is the analytical length and is defined under Huaren in peridynamics. The interaction between two mature points can be described by a macro-modulus function. And this function includes the mature point information, and the fracture information can also include in this function, such as the commonly used bound breakage function. In this function, if the stretch reaches to a limit value, and the interaction between the 2 points will disappear. Based on this bound breakage function, they defined a damage function like this. It is similar as the non-local average operator as we proposed, as we introduced before. For the bound-based peridynamics, they assumed that the bound between two mature points is independent with each other. That means not the interaction between different boundaries. Based on this assumption, there is a limitation. That means that the Poisson ratio is equal to 1025 in three-dimensional problems. In order to solve this limitation, Sterling further proposed a state-based peridynamics. In this theory, he used the state to represent the deformation and force. While the force state can be determined by the constant model, it also includes the mature property information. So by the concept of peridynamics, we can obtain the inequality based on the second law of thermodynamics. In this inequality, T is the force state and Y is the deformation state, theta is the temperature, and eta is the entropy, and phi is the free energy density. For the free energy density function, we assume that it is related to the deformation state, temperature, and the damage state. The derivative of phi with respect to time, we can obtain the function like this. We invoking this function to this inequality, we can obtain the inequality like this. From this inequality, we can obtain the three equations. It means that the force state can be obtained, and the force state, the entropy, and the D means the damage energy release rate can be obtained from the function of free energy density. Because of the damage is irreversible, so we can obtain a restriction of the damage state like this. Alright, we further define a free energy density function like this. In this function, phi 0 represents the spring energy density of an undamaged model. By this assumption, we can obtain that the force state is like this and the damage energy release rate like this. Well, we define the damage state omega is a function of D because we can find that here D is non-local, so this function also is naturally non-local and it depends on material property and the condition of loading. So it may have many forms. Let me give some details about omega and D. So for the detailed calculations, we can obtain the D from the peridynamic string energy density like this. And for damage state, we can give simple examples. For example, like this. In this function, the parameters B, D1 and N is depend on their detailed material property and the condition of loading. In our next simulation test, we select B and N is equal to this, and the D1 is the responding string energy density when the string is equal to this. When D is larger than D1, the damage occurs, otherwise the damage not occur. So based on the framework we proposed before, let me give some cases. But the first case is about damage evolution. In this case, we give initial velocity conditions, and from different types, the damage results are plotted in these figures. From these figures, we can find that when t is equal to 0.35, the damage localization is paired, and after this time, the damage localization remains, and the zone of the damage increases. We investigate other characteristics of the damage evolution. For example, when the non-occurrence is unchangeable for different grid density, we can find that the damage state is always the same. It means that the damage state is independent of the grid density. Well, it shows that our non-local model overcomes the grid density, and for another cases, we can find that if the non-local, if the grid density is not changeable, and for different non-local lenses, we can find that the damage state is different. Especially as the non-local length decreases, the damage state tends to localize. Well, for the displacement control cases, we can find that we can easily obtain the load displacement curve as we introduced at the beginning of the presentation. Similarly, when when the grid density increases, the damage state also independent of the grid density. And when the non-local length is changeable, the damage state is related to the non-local length. Well, we also calculate other complicated loading cases, such as with unloading and reloading conditions. We can obtain the load displacement curve that references the actual loading conditions. And for the load control conditions, we can also obtain the two characteristics of damage models. That means that the non-local state is independent of the grid density, as shown in these figures, and the damage state is related to the non-local length, as in these figures. So these are basic numerical tests. Now at the last, let me give simple conclusions. In this work, we proposed a non-local damage model and to simulate the string sorting phenomena. In this model, the governing equation and the damage parameters are non-local. And the non-local parameter model overcomes the grid density we can see from above numerical test. And this parameter model can be extended to cases involving fracture and damage, and maybe some other complex loading conditions. Okay, that's all my presentation. Thank you, everyone.
Thank you very much for the nice presentation. I think Peridynamics is a very nice framework to calculate non-local damage in materials. But do you have, I have two questions. Do you have some comparison against some simple experimental results, at least for a displacement control case? Another question is, how do we determine this non-local length L?
Well, let me answer your first questions. We haven't do any comparison with the impairment date. You can see in our presentation that we just make a simple assumption about the damage statement. We know that it is related to the material property and the condition of loading, but we have didn't do the applications of our models based on our next future work. And for your second questions is common questions people will ask about the non-local theory. Well, fortunately, we can from this work of study. In these papers, he gives the detailed questions that how to calculate the non-local length. It is related to the parameters of the microstructures, and also related to the size of the structures.
Thank you very much.
Well, thank you.